So section 4.2, logarithmic functions. So what I want y'all to note that first of all, before we even go over to the definition, and obviously there's some notation of logarithmic functions and forms, I do want you to know that a lot of times people feel a little bit overwhelmed with logarithmic functions, and it's just probably because a lot of times they don't recognize the notation. So the notation in this section is super, super important. And all I want you to know about logarithmic functions thus far is just that logarithmic functions are a way to write a number that is an exponent, but in a very small form, in a condensed form. So think of logarithms as making those exponential functions that have, a ton of numbers to them, just simply a smaller form and a condensed function. Okay, so in this definition, we want you to know that you can go from the logarithmic form to the exponential form, and you should be able to do this, especially if logarithms are actually exponentials. Okay, so you can go to both forms. It's just one's, again, written in a condensed form as opposed to the other. So here, it says that, okay, so what we want to be able to write in both ways are these two things. So what this is saying is that these can be swapped out at any moment, okay? So notice what this is saying. So what this is, it says here that this is the function f of x equals log base b of x is the same logarithmic function with base b, okay? So what I want y'all to note is that this is not b times x, okay? This little b here means a base b, and we're used to seeing that base b in exponential functions in section 4.1. So within that base b, notice that base in exponential functions is the biggest number that we see, and of course the exponent is the smallest number. And in this scenario, that if we look at the exponential form over here, so where it looks like an exponent, we have a base b raised to the y power equals some number x, okay? So notice that the y here is the exponent. So that means that we have a y here as an exponent. Right? So the way that we say this is that we actually say log and then base b of x. It's not log b of x. It's log base b of x. So in order to say this properly, remember that log base b of x simply means that you're going to have a logarithmic function written all in terms of x, okay? Also, I want you to know how to write this. So I don't want anyone to be writing this to where it looks like you have b times x. So just practice our handwriting on this. Remember to make that b a little bit smaller and a little bit beneath the log. Okay, whereas x should be the same height as the other letters in the word log. All right, so as you can guess, that there's a lot of different bases. Actually, there's infinitely many bases, isn't there, for log? You will see later on two important bases that are actually called something special. But we won't get to it for another couple of slides. But we are going to practice looking at what that means as far as our calculator as well. Just so you know that we will in the future have that involvement in our calculators. Okay, so now we know that Logarithms are a simpler or condensed form of writing exponentials. Then, and also that we know what the definition is of a logarithmic function, and we know how to say what a logarithmic function is, and we know how to write one. Well, now I think it's time to go and play around with all the different notations for the logs and also the exponents. Okay, so notice, in both of these, b is the base. So in the logarithmic function, b is the base. In the exponential form, b is the base. So the exponent in the exponential form obviously is higher. It's, it's higher than that base, meaning you have a base raised to the y. Okay, so it's the exponent or power. Now over here in the logarithmic form, notice that the exponent, that's what that whole entire log is equal to. Okay, so you want to think about the x's and y's switching back and forth from the equal sign. So let's first of all, let's kind of get this down, this idea down about what this looks like and what this is, especially in two different forms. Okay, so for the logarithmic form, we have log base 2 of 8 equals 3. Okay, so I know that for this moment right now, some of you guys might be like, would never have any clue that that would actually equal 3. Okay, so the logarithmic form, again, is a little bit alien to us. We haven't seen it very much. So when we change it to the exponential form, that should look okay to us. We've seen something like that before. We're familiar with it. So, our stress level probably goes down when we see something like a log written in exponential form. So you definitely want to be able to create that log in exponential form. So when you look at this log base 2 of 8 equals 3, then we immediately put the base down in the exponential form because that's the biggest part of it, right? So remember that our base is exactly the same in the log function as it is in the exponential function. So we're just going to go ahead and write down 2. So that's our base. And remember that the exponent is what the log of all this stuff is equal to. So you have raised to the third power equals, and then whatever's inside that logarithm is what the exponential function is. So you have 8. And see how this makes a lot more sense, because in this exponential form, you're like, oh, well, yeah, that makes sense, because I know that 2 times itself 3 times is going to be equal to 8. Now going backwards, what if you had to write the exponential form here into the logarithmic form? You still, in the very beginning, note what your base is. So the first thing I write is going to be log. And then my base b, in this one, my base is 5. So I'm just going to put down base 5. And then I know that this is my exponent here, so I know that that goes out here. And the only other place is inside this log. So I got log base 5 of 25 equals 2. And again, looks a little bit more familiar in exponential form. Okay, so in this one, things are kind of switched up a tad bit, but you should still be able to work through this okay. Because first of all, you have your base b, even though it's not a particular number, you can still write that base b down. And remember, our exponent over here is where it equals the whole entire log. So there's our 3 and equals whatever's inside the logarithm, which is 64. So just out of curiosity, you guys, can you think of a number multiplied by itself 3 times to give me 64? I can kind of go down the line of like 2s. Like I know if I multiplied 2 by itself 3 times, that's what? 8, right? That's what we saw up here. If I multiplied 3, let's see, 3 times 3 is 9, and then 3 times 3 is 27. So that's not 1. But then if I reach 4s, I've got what? 4 times 4 is 16, times another 4 is 64. So we didn't need to solve this out, but just so you guys can kind of see what's in store for you ahead, note over here that b is actually equal to 4. That base is 4. And I'll throw a little thought cloud around it since it's just kind of a thought for right now. So exponential form to logarithmic form. So I have this base b of 12, so I have log base 12 of x equals 2. And here my base is 3, so I have 3 to the y equals 7. So those are all the different types of forms that you can have going forward to backwards and so on. Okay. All right, so let's get this down to where we're going to be able to start to actually view and see what values are. Like in before when we had things like this. Like after a while I want you to know, and let me make this a little bit thicker. What they'll do is they'll say, hey, find the value of this, which is something that you're going to have to do. But of course, we can change it to the exponential form, which is always a good step if you're not really familiar with the logarithmic form. So I want you to know that you will, many of you, especially by the end of this video, should be able to look at this and immediately say, oh, that's 3. Okay. Many of you guys over here looking at this, by the end of this video, y'all should be like, oh, okay, that's 4, right? Other than y'all are doing it now just because I told you what the answers were. But, what happens with this, and let me erase this real quick so y'all can have it. What happens, the first thing that we want to know about this is that if the bases are the same, then the exponents are equal and vice versa. Then you're like, okay, well, what does that really mean? All right, so if the bases are the same, so let's write 2 bases that are the same. Let's say 2, okay, equals 2. All right, so well, this looks pretty true right here thus far, right? But then the exponents are equal. So if I said 2 to the x equals 2 to the third, well, guess what x is going to equal, you guys? It has to. It has to equal 3, doesn't it? Because I know that 8 has to equal another 8. So in order to make this true, we know that the exponents are equal. So bases are the same. And bases are equal. So x has to equal 3. And vice versa. So that means that the exponents are the same. So if you had like x raised to the 4th equals 5 raised to the 4th, well, guess what? X is going to equal 5. Because 5 raised to the 4th has to be the other side of 5 raised to the 4th also. So here exponents are equal. So this is what they're going to do. So I kind of took these out of the book. You can see that they're a little bit highlighted in this gray area. So I wanted you to figure out, well, how can I manipulate this in order to make it look reasonable? Well, first of all, what we can do is if they ask us what log base 2 of 16 is, some of us don't know. And if we don't know this, then we have to put a variable with it. And what we've seen before is that we've seen a log function, sorry guys, we've seen a log function equaling y. So that's exactly what we're going to do. So now we have these variables and numbers and functions floating around. We're going to go ahead and put that into exponential form so you can see exactly what's going on with this. So to put this in exponential form, remember that y is the exponent and 2 is the base. So I have 2 to the y equals 16. Okay. Then you start thinking to yourself, well, what do I have to raise 2 by in order to get 16? And you start kind of going through it in your head, like, oh, well, there's, 2 squared, which is 4. There's 2 cubed, which is 8. There's 2 to the 4th, which is 16. So what you want to do is that you want to get both sides in the same base. So here's a detailed part of it. You could, at that point, you can say, oh, well, of course, 2 to the 4th equals 16, so all of this has to equal 4. But what you want to do is you really want to utilize your skills for actually being able to make both sides have the bases that are the same. So we look at here, and we know that 2 and 16 have a common base of 2. So you need to be able to find the common base. So finding common base, you've got 2 to the 4th equals, sorry, not 2 to the 4th. I want to say 2 to the y. I don't want to change anything over there. 2 to the y equals then 2 to the 4th. And so then, because both of our bases are the same, we can use this rule. Bases are equal, so that means that the exponents can be set equal. So we have y equals 4. And so that means that all of this is simply 4. So the log base 2 of 16 is actually the value of 4. This one is a little bit more difficult because you have to remember your use of negative exponents. Okay, so if you have something like this and you don't know what it is to begin with, and that's perfectly fine, you can say, well, this equals y. And this is a different question. So I'm going to go ahead and put this in exponential form. So I have my base, which is 7. I have my y, which is my exponent, and then I have all that equaling 1 over 40. So now we want to find the common base. So here, notice that 7 and 49 have a common base of 7. So I can rewrite 7 to the y as 1 over 7 squared. And notice I didn't put it up in the exponent yet. And the reason why I didn't put up in the exponent yet is because I kind of didn't want to do 2 steps at once. I really wanted to get down the common base first and then start moving things and manipulating things around. Okay, so I have 7 to the y equals, and if I move this from the denominator to the numerator, remember that it changes the sign of only the exponent. So you have 7 to the negative 2. So we have y equals negative 2. And so that means what I can do is I can go over here and erase this y and say, hey, well, log base 7 of 1/49 is actually negative 2. Okay. So moving on, let's look at the graph of exponential and logarithms, okay, on the same plane. Right, so this is super important right now. Notice that that there's that line y equals x, right? And we just kind of went over this. Actually, we didn't kind of go over it. We went over it in detail, right? So notice that, if it's reflected across the line, y equals x, and that function has an inverse. And guess what that inverse is? Yep. Logarithms and exponential functions are inverses of each other, in fact. Okay. So this is a good idea to think about. That these are, remember, your identities, your inverse identities. And remember, the inverse identities is what you do when you check for to see if you found the inverse correctly. Okay. So just kind of giving you this idea and setting it up in your head, like, Oh, okay, that makes sense. So it's a graph there, and notice that this is the log function because these two x's and y's are switched. It's reflected across the line, y equals x. So yes, they're definitely inverses of each other. And of course, not only that, you can change one form into the other as well. Okay. So what I want to get to you across to you is that note that if the exponential and logarithmic functions have the same base, then they equal x if composed of one another. All right, so that's basically the shorthand for this. But this is what I want to show you. And I don't know if I put enough room in there. No, I didn't. So let me go ahead and add a nice slide to this. The slide to add is that, say that you have your regular function, which is your log function. Okay, so log base b of x. Okay. And let's say that you have your inverse function, which we know that the inverse function of a logarithmic function, according to that graph, especially to that graph, we know that that's b2x. Okay. And we know our identities. We know that f of x composed of its inverse is supposed to equal x. Also, that the inverse composed of its function f of x is supposed to equal x. That's how we check our answers, especially in section 2.7. So this is the stuff that we learn in 2.7 is coming in really, really handy for section 4.1. Sorry, 4.2. So this is what I'm going to do, just so that y'all will notice this and reflect on what we just said about the bases being the same. I'm going to go ahead and do this one here, to where I'm taking everything in the inverse and plugging it into that x there. So I have log base b of b to the x. Okay, that's what I've got so far. This is when I plug my inverse into my regular function. And so notice, out of this whole thing, I'm supposed to get an x. And this makes sense because notice, both of my bases are the same. Okay, so if both of your bases are the same, they cancel each other out because you guys, they're inverses of each other. So the only thing left is just simply x. And likewise, if I try it in the other way, if I plug in the regular function into the inverse, I've got my regular, I have all of this stuff now being plugged into that little x. So now I have base b raised to the log base b of x. So note that these bases are the same. And by this here, that has to hold true, so that's x. Because notice, these bases are equal to each other, therefore they cancel out because they're inverses of each other. Think of some other inverses that you know, like the square and the square root. If you put one inside the other, then those cancel out, don't they? If you multiplied by 5 and then divided by 5, they cancel out, and you only have one left, right? So think about it as, you know, being the inverse, doing the opposite of what it says. So if I'm taking a log, then that means if I put an exponent in it, it's just whatever that exponent is. If I take an exponential function and then stick a log in it, it's whatever's inside that log. So it's whatever that x is. So with this whole idea, let's practice this. So this is the point at which you're going to start beginning to feel a little bit more comfortable with being able to look at a log and automatically know what its value is. Okay, so I wrote these things up here for you guys. So note that you have the base b's, as long as those are equal to each other, then it's just x. These bases are the same, so it's just that x. So if we look at this first one, notice the base of the logarithmic function is 4. The base of the exponential function is 4. So let me rephrase this in a little bit more detailed way. I'm going to put a highlighter around the log. Okay. This is the log function. Okay. This is the exponential function. Notice how the exponential function is inside this logarithmic function. And notice that they have the same bases. So same bases. So what I'm going to do now is I'm just going to cancel this out. And all I have left over is my answer, which is 6. Notice it was in this form here, and we took whatever was in the exponent. So you can look at this and be like, oh, well, that's 6. This next one is in this form here. We've got this base. Here's the sorry, I'm getting tongue-tied. Exponential function. And here's the logarithmic function. And notice they have the same base. So same base of 7. So what's my answer? 23. This one is a little bit more difficult because it has that base 11 of 11. And we have to write the implied parts. The implied part to this is 1 up here. So note that these bases are the same. So all that's left over is just 1. This is the trickiest of them all because we're thinking, oh, well, how do we write 1 as a base of 6? Well, log base 6, and then I can rewrite this as 6 to the 0. That's where it gets really, really tricky. Anytime that they give you 6 to the number 1 or 7 to the, or any log to the number 1, it means that it's just simply 0. Because anytime that you have the number 1, you can write 1 as any base as long as you have the exponent of 0. Because remember, x to the 0 is just simply 1, no matter what number you put in for that x. So since both of these bases are now the same, I can say that equals 0. So don't try to think of these in every different light. All you have to do is just think of the rule. If both of the bases are the same, then it's whatever that x is. Okay? But both bases have to be the same. And the bases that I'm talking about are with the logarithmic function and the exponential function. Okay? All right. So moving on. We have a couple of important logs. Notice one of them is a common log, and one of them is a natural log. So you will see this on your calculator, and I want you to be able to see this. You have a common log. Notice that you just have this button, LOG, common log. That is a base 10. Here's your ln, natural log, has that base e. Okay, so those are those two buttons there. All right, so just getting into this, and I just wrote this down that it has a base 10, that it has a base e. So let's talk about how this really looks. So a common log looks like this. And it looks like the base is completely gone. Okay. So remember at the beginning of the semester when we were discussing all the implied things um, around a number? Like remember if we had, like the number 4, 1 times 4 over 1 to the first, all those ones are being what? Implied, right? And there's a reason for that because I wouldn't want to have to write, as much as I write in math, I would hate to write all those ones down. And there are more ones there, if you really want them to be there. But that's a lot like with the common log. The common log has a base 10, it's just not written. And the reason why it's not written there and it's just, one of those little implied numbers is because we live in a base 10. And you're like, how do we live in base 10? Okay. So note that our digits that we use are from 0 to 9. Okay. Those are 10 digits. And if you don't believe me, you can count them on your fingers. Just count 0 to 9. So they're 10 digits. So we live in a number system of 10, okay, of base 10. Now I can say that if you get into computers and things like that, you might live in a base 2 to where everything is 0 and 1, okay? But as far as right now, we're just talking about logs. We're just living in the base 10. So the way we want to think about this is that it will be written as log and then space x. Oh. This is what we want to think of. Here's my little thought bubble. That you want it to look like, oh, I know that there is a base 10. So I have log base 10 of x. That's all that means. Okay, so now we're looking at these and we're like, well, what are all these values? Well, I think it would be really good is that if we put the implied stuff there. Now, I want you to notice that this 10 here is not a base. Well, okay. Let me correct myself for this one. This 10 is the base for the exponential function 10, base 10, raised to the 8th power. Now, for this log, there's nothing there, meaning that this is a 10 down here, but this 10 doesn't act as the same base as this. This is 10 because there is nothing there, meaning that it's the implied stuff. So the way I'm going to write this is log base 10 of 10 raised to the 8th. And I'm just going to go ahead and put these in parentheses just to kind of divert your eyes away from that other 10 because you need to acknowledge that, yes, those 10s mean different things. This 10 is the base of the logarithmic function. This 10 is the base of the exponential function. So y'all, those cancel out because they have both the same bases. So we have 8. So the common log of 10 to the 8th is just 8. This one, again, we can write in that 10 there. We've got 10 log base 10 of 53. Well, both of my bases here and here are equal. So that means I just have 53. This, I've got log of 1,000. So that means that I can make this actually equal log, and I want to put these as a base 10, don't I? Because it would be much easier. So 1,000, so 10 times 10 is 100. So that's 2 10s, and then times another 10, a third 10 is 1,000. So I have the common log of 10 to the third. And it's kind of like this one over here. Some of y'all can already see it. If you said 3, you're correct, because I have log base 10 of 10 raised to the third, which equals 3. Okay. So you can manipulate these things as long as they have the same base. Okay, So here, my natural log has a base e. So the way it's going to be written, notice you have the ln on everything. So this is the way it's going to look written. It's going to look that way in your book and so on. Another way it can be written, and this may be an easier way to think about it, is that you have log base e of x. Okay. These two guys mean the same thing. All this ln, it's nothing very magical other than the fact that it can transform itself into looking like two different logs. So you've got this natural log of x, which is the exact same thing as just a regular old logarithmic function with a base e. And you guys remember that e is approximately 2.71, right? Okay. So here, let's write it, because a lot of times I don't want you guys to get confused about the natural log. A lot of times students will look at natural log and e and think that they're completely different bases and they're completely different things, and nothing should ever cancel out of them, and so on. And that's not necessarily the case. If you have a natural log mixed with an e, thank your lucky stars, you can cancel something out. So you've got equals e to the log base e of 300. And note that these bases, this e and that e, are the same, so I can cancel those out, and it just leaves me with 300. So instead of even writing it like this, you may be able even just to go ahead and be like, oh, well, I don't have to write it like that. As long as you see a natural log and an e right beside each other, we'll just go ahead and cancel those things out. So if I were to move this e to the 6 up to the numerator, I would have this natural log of e to the negative 6. Well, this natural log and this e are right beside each other. They're inverses of each other, so I know that all this whole entire thing equals negative 6. Here, I've got the natural log of e, and I can say, oh, well, that's just natural log of e to the first. Well, these guys, remember, this is just the implied part. Those guys cancel out, and I know that it all equals 1. And if you wanted to get even further along with it, guess what natural log of 1 is? Just to kind of mess with your head a little bit, I've got log base e of e to the 0, because e to the 0 is just what? 1, right? Natural log of it. So those cancel out, leaving me with 0. So again, even natural log of 1 is still 0. So y'all, I want y'all to know, anytime you have a log of 1, it will be 0. And you can put it in this form if you need to. Okay? So if you notice throughout your book, there's a ton of rules. The only things that you really do need to write down are these. Okay? If both bases are the same, then it's whatever's in the exponent or whatever's in the log function. Okay? You might want to write down common and natural log in these particular forms to remind yourself on the test. That's another good thing that you might want to put on the note card. Excuse me. Okay, so graphing logarithms. What we've seen before is that we know that the exponential function and the logarithmic function are inverse of each other. Okay, so what's interesting about this is, first of all, let's go ahead and write this stuff down before we get there. This is what you're going to come in contact with. So you're graphing logarithms now, you guys. Okay, we do have two important points, just like we did before with the whole transformations in section 2.5, as well as the transformations in section 4.1. with those exponential functions, which we probably need to go back to the exponential function. So notice here is that in this exponential function, we always have the point 0, 1, and then we have also the other point 1b. Right? So those are our 2 points that are super important. Now, for the log part, since they're inverses of each other, this means that instead of 0, 1, I have to have 1, 0. So now instead of 1b, I have to have, you guessed it, b1. So check that out. So when we go back to this, writing this out, putting it on the proper slide, we've got the 2 points, 1, 0, and b1. Okay. So again, remember, just switch the basic points of the exponential function, and you'll have the basic points for the logarithmic function. Now, instead of a vertical asymptote, we have a horizontal asymptote. Sorry, instead of a horizontal asymptote, we now have a vertical asymptote, because check this out. And remember that whenever you're graphing something or you're looking at inverses of something, you know that the x's and y's switch. So this is a y equals 0, because this is that horizontal asymptote there, that dotted line. Now we have a vertical asymptote because guess what? My x's and y's switch. So that means that on my horizontal asymptote, my y switched to my x. So now I have x equals 0 for a vertical asymptote. So that's where that comes from. You're trying to figure out why I have a vertical asymptote. So I have x equals 0. So remember, the domain for exponential functions was negative infinity to positive infinity. So this means that my domain was on my x's. So this means that now, because I have the inverse, which is the logarithm, it means my range has changed. So my domain for my exponential function is now my range for my logarithmic function. So my range is going to be from negative infinity to positive infinity. Now my domain is going to start with 0, aka the asymptote, and then end with positive infinity. So in this scenario, in my logarithms, I know that now it's not the range that begins or ends in the asymptote like the exponential functions. It's now the domain that begins or ends in the asymptote as a logarithmic function. Okay, so let's just plot this. We've got domain 0 to positive infinity. We've got a vertical asymptote of 0, so I'm just going to write down 0 over here. I'm just drawing a little dotted line. Trying to make it look kind of hashed up or whatever. Because I definitely don't want to draw the graph over it or on it. I just want to draw the graph close to it. So I got the point 1, 0. And then b1. And remember that b is our base of the logarithmic function. So below the x-axis, I'm going to get really, really close to that asymptote. And above the x-axis, I'm going to go away from that asymptote. Okay. And so we see here that my lowest x value starts here at 0 and then goes over to positive infinity. But remember, not including 0. And then notice my lowest y value is way down here at negative infinity, and it keeps on going up and over. So the more and more this keeps going this way, the more up it goes, even though it doesn't look like it. Okay. So the further that it goes in this direction, it's still going up and out. Okay, so it's still going up. So negative infinity to positive infinity. Now, be super careful about this. Please do not get this mixed up with the graph of the exponential function. It happens more than you know, almost all the time. So practice, what I would do if I were you guys, I would honestly maybe print out some problems, like just look in the book and or even on your homework, print out some problems um, and make it a mix, like literally make it a mix of either logarithmic functions and exponential functions and throw them in a hat. And pick out one to see if you can graph it from beginning to the end. And hopefully a logarithmic function will not accidentally turn into an exponential function. Okay, or vice versa. Okay, so practice each one independently first and then kind of mix them together and see if you can decide which one is which and which points go with which, because you need to keep them separated, because in this particular section it's very easy because you just do one switch and then that's it. You've lost it with the whole inverse idea. Okay, so be careful. Okay, so practice really hard on this. All right. So this one kind of has a nice everything in it type of problem. So first of all, we need to pick out what the basic function is, because when we have the basic function, there are two things that we know. We know our points and we know the shape of the graph. So my basic portion of this is just, here's my basic portion. Log base 2 of x. Simple enough. Okay. So we have, first of all, as always, writing down my set of axes. And notice here's my basic, but then this does something to it, this does something to it, and then that does something to it. So there's three things. So I have my basic graph, and it looks like I have three other graphs after that. Okay. So what I'm going to do is I'm going to label them. I've got my log base 2 of x. Next, I note that this negative on the outside of the function reflects across x. Okay. So I'm going to deal with the reflection. So I got negative log base 2 of x. Then I've got this plus 1, and note that this plus 1 is on the inside of the function. Therefore, I know it shifts left 1 unit. So this means, remember, you're subtracting all of your x values by 1. So you've got negative log base 2 of x plus 1. And then this plus 3 out here means that you're going to have a vertical shift. It's on the outside of the function, so you're going to raise everything up by 3 units. So up 3. So this is where we write our last little part here. We know that this is going to be the graph that we want. So log base 2. It looks like a lot, doesn't it? But if we take this step one at a time, we will get this graph, and we will get this graph perfect. So our 2 points. But first of all, before we even get to the 2 points, remember our asymptote. So our asymptote, what I'm going to do, I'm going to go ahead and write this down, that x equals 0. Okay, so that I can say it through each one of these, and so that I'll always know what my asymptote is and I never have to guess at it. And so then I've got my point, my important point. I've got 1, 0, and then I've got 2, 1. And wait, how did I get that so fast? Remember, always 1, 0, and then b, in this case, our base is 2, and then 1. So 2, 1. And of course, below the x-axis, I'm going to go close to the asymptote, and above the x-axis, I'm going to go away from the asymptote. All right, so notice here I'm reflecting across the x, which means I'm negating all of my y values. And let me go ahead and write these in because that's not good for me not to write these in. So if I negate all my y's, it means I am changing the sign of the 1 in the 0.21, and I'm changing the sign of 0 in the 0.10, which doesn't make a lot of sense because if you negate a 0, it just means 0. So negative 0 is just 0. So this means it doesn't change anything for this 1, 0, but it does change for this 2, 1. It's now 2, negative 1 because I just negated all of my y's. So I've got 2 and then negative 1. And so I still have to draw my asymptote, and notice that this is x equals 0, doesn't have anything to do with the y's, so it remains the same. Okay, so the way you want to draw this is that beforehand, everything's changed now. Instead of beforehand, when we were having the bottom of the lower level of the x-axis, beneath it was getting close to 0. Now above it has to get close to 0. Okay. And before, when above it was going away from that asymptote, now below it goes away from that asymptote. Okay. So it's the same characteristic, but see, this is where it starts getting kind of hairy because people are like, oh, it looks like the exponential function. It is not the exponential function. Be very, very careful. Just note that it's just a logarithmic function, but it's reflected across what? The x-axis. So here, because of this plus 1 here, I'm going to go ahead and then subtract 1 from all my x's. So from here to here, oh, one thing that I forgot to write, always write your asymptote, it helps. So from here to here, we are going negate all y's. From here to here, we're going to subtract 1 from all x's. So instead of my point, well, actually, before we even do that, we don't even want to discuss points yet because this asymptote is our x. So if we subtract 1 from 0, it lands on negative 1. So this means that our asymptote is a new asymptote at x equals negative 1. Now see, we created this this little nice boundary here. Okay. So over here we've got this 1, 0. When we subtract 1 from that x value, it becomes 0, 0. So I just simply move it to 0, 0. And instead of 2, negative 1, I subtract 1 from 2, which becomes 1, negative 1. And of course, it does the same thing. We didn't have any reflections. So above the x-axis, it goes close to the asymptote. Below the x-axis goes away from the asymptote. Okay, so then from this graph to this graph, our transformation is to move it up 3 units. So what we're doing is we're adding 3 to all y's. Okay. So if we add 3 to all of our y's, this means that the point 0, 0 now becomes 0, 3. And note that I didn't change my asymptote here. I haven't drawn it yet. I'm just writing down the point. Didn't change anything on the x equals. So we've got 0, 3. And then we've got negative 1 plus 3 gives me a positive 2. So I've got 1 and positive 2. And don't forget our asymptote at x equals -1. And so now to draw my characteristic of the graph, I know that above the first dot is close toward the asymptote, away from the asymptote, going through the second dot. Okay, so you will be asked your domain and range in this scenario. Now remember, the domain and range aren't always going to be what they seem in the beginning. The domain here of this particular function is going to be from -1, so here's -1 all the way to positive infinity. So excluding that -1 going to positive infinity. Our range of this function is going to be from -infinity all the way to positive infinity. Because remember, this looks like it gets close and close to 0 and doesn't touch it and such, but it actually crosses it. Just want you to know that in a logarithmic function, it will cross this x-axis from time to time. Of course, obviously, look, that's what happened in the past two, or the past three graphs, right? So it will cross. So just note that it goes from -infinity up to positive infinity. Now I can say that for some logarithmic functions, the range isn't always negative to positive infinity. I could give you a tricky question for that bonus one. So think about ways that a logarithm could not be negative infinity to positive infinity as far as range goes. Okay, so good question. Okay, you guys, so that's one with everything in it. And again, you will at most have, two things that you do to it. Okay, just so you know. I always try to give you all the harder ones so that when it comes to tests, it's a little bit easier. Okay, now that we've gone through all this stuff, and now you're like, oh no, we have to find the domain of these logarithmic functions. All right, I want y'all to know something. That the cool thing about logarithmic functions and finding the domain for those is that all you have to do is just set whatever is inside of those parentheses strictly greater than 0. Because guess what? This is what I'm going to do. I'm going to go into my calculator and I'm going to be a student for a second. And I'm going to be like, oh man, okay, so this is a test question. Of course, I don't see any of this stuff up there, right? I'm just like thinking to myself, okay, I got to find the domain of this thing. All right, so if I remember correctly, I'm not sure if you can take if you could take a log of a negative number. So let me just go ahead and try it. If I do like log, say -5. Oh, that's a math error. It means it's a domain error, meaning that's not something that it's undefined. This would be undefined if you were to take a negative, if you were trying to take a log of a negative number. Okay, so you can't take the log of a negative number. So now let's just say clear, and let's try to take a log of 0. So what if I did log 0? Oh, that's a math error too. Well, let's just try like log of 2. That means that every single item inside of here has to be strictly greater than 0 for it to work. Now remember, this is not solving this whole equation, and it's not finding, x-intercepts or y-intercepts or anything like that. It's just saying, hey, what x values can I plug in here for the equation to actually hold true? Okay, meaning, what can I put in there to where it won't be undefined? So I'm going to say, well, x plus 6, all that stuff has to be greater than 0 because we've seen what happens when we try to take a log of a negative number or a number with 0. So now all we have to do is just move the 6 over, and we got x is greater than -6. So we can say, hey, the domain of this particular function f is going to be equal to the smallest number being -6 and the largest number being positive infinity. And if you're a very pictorial person and you just need to draw the graph, by all means, we've got a big hole there, so it's the circle, and so all the x's that are greater than that. Okay. So just remember, domain is just setting whatever's inside of this function strictly greater than 0. Okay, y'all, that is it for today. So, wow, we've gone through a lot. Awesome. So by now, you guys should be able to look at a logarithmic function and be like, okay, I can see it as a manipulated form, looking for the same bases. You should be able to graph it. You should feel comfortable with knowing that common log is a base 10, natural log is a base e, and so on. So let me know if you guys have any questions. This is a very, very, very important section. It will help you through the rest of the sections of the book. Otherwise, I will see you guys next class.